Alright everybody, I think you'll like this one. This is more for fun than anything. I have the fish tank set up here with the same gradient. I got just fresh water up here, maximum brine down here, and as strong a gradient as I can get. But I have here a little RGB laser. It's got 3 lasers, a red, a green, a blue, and then it uses little color selective mirrors to combine all 3 colors so that it forms a basically coaxial beam with all 3 colors all lined up with each other. So there's the spot it makes. It's pretty well one on top of the other, really, for a cheap Chinese eBay product. Alright, let's turn the light out. So you can see there's my basic beam going across the bottom there. But watch what happens when I tip it up. Start to tip it up. Let's just do a... This is more representative of a... This is representative of like a Snell's law boundary, a simple boundary refraction. We have it in the more dense medium here, then it goes to the less dense medium, and it refracts. I hope I said refracts. Anyway, it refracts around or a little bit, and then goes straight up in the freshwater. But look, we are getting chromatic dispersion or aberration. So we're getting a little bit here probably because it's entering the glass at an angle, but it's not much. But right here, where it starts bending in the gradient, we can see that the 3 beams are separating out amazingly. And they really do separate out too. But now let me just make this more of a glancing blow. Look at that. So now let me back up so you can see the whole picture. That's the general path. You can see they start separating right here quite a bit noticeably. Then by right here in the middle of the tank, they're highly separated. But then over here, they get even more and more separated, with the red the last to start bending, really. So I thought that was kind of interesting. Let me bend it down a little more. Down in here, this is a more gradual bend, and so it's not causing as much dispersion. But right when it's going through that really strong gradient right there, what's interesting is, look at this. The red is, because of its longer wavelength, hasn't reached its critical angle. So it actually... Oh, this is interesting. Okay, so you've heard of total internal reflection. And that means that the ray of light is coming up, it hits this gradient zone, and it bends. And if it bends too far to come back down, and it never crosses through the boundary, and it's trapped in total internal reflection. But the critical angle depends on the wavelength. So you can see the blue followed by the green, they bent enough to be trapped. They were totally internally reflected, but the red was not bent enough, and it escaped through the boundary and then continued on its way. So that's kind of interesting. This also explains the rainbow fringes that we saw in some of my other videos. I wonder if I can get the just the blue to trap. Go up a little, oops. Oh, yep, there. Yep, now I got the green and the red are escaping, but the blue is totally internally refracted. So, what do you think of that? Come on, focus. There you go. This phone is very old. Very, very old. I got it used old, but hey, if it keeps ringing, right? Alright, enough of that.